So we're going to talk about Robert Hooke, who has been referred to as London's Leonardo. And I've included two of his illustrations here. I'm sure the one on the right is familiar to you. It's the center of the moon. The one on the left I was a little worried about, whether it would be familiar in Abu Dhabi. So I Googled to find out, and I found in the National in January 25th, 2009, that in Ras Al Khaimah there was snow on Jebel Jais area for only the second time in recorded history yesterday. Aisha al-Habsi, a woman in her 50s who has lived in the mountains near Jebel Jais all her life, said snowfall in the area was so unheard of that the local dialect does not even have a word for it. Hail's known as barad, which literally translates as cold. 20 years ago, we had lots of hail, said Ms. al-Habsi. Last night was like this. At 4 in the morning, we came out and the ground was white. Jebel Jais was dusted in snow also on December 28, 2004, the first snowfall in living memory for Ras Al Khaimah residents. So this struck me when I found it because of the date, December 28, 2004, for the first snowfall in living memory, because that was the end of the first semester at Yale in 2004, and the second semester I had a leave coming, and I work on crystals, as David said, so I was looking for something interesting to do about crystals, and one of the most beautiful crystals is, of course, a snowflake. So I got wondering, who was the person who first drew an accurate picture of a snowflake? So Yale has a wonderful rare book library, so I went looking. So in 1555, Olaus Magnus, as it says here, formerly the Archbishop of Uppsala, but he got kicked out after the Reformation when the Lutherans took over and took refuge in Rome, and wrote a book of many, many chapters, I think there are 250 chapters, about different things about life in the north that these people should know about. For example, chapter 23 is about the snow castles of children, and it shows them having a snowball fight here. And chapter 22 is on the various shapes of snow. So there are three panels here that show, the first one is frost on windows of the kind they had in 1555. And the second one is a view of a snowstorm. And the third one is snowflakes. They're pretty imaginative shapes for these snowflakes. But one of them at least has six-fold symmetry. So there's somebody probably had seen that one at least. But they're not really very accurate. So about half a century later, there was snow at Prague Castle. And walking through the snow in 1610 was Johannes Kepler, who then in 1611 wrote a New Year's gift on six-fold snow. But he didn't show any actual flakes. What he showed were these figures, and what he was trying to explain was how it has hexagonal symmetry, which you would expect from the packing of spheres, so not realistic snowflakes there. This was a period that was known as the Little Ice Age in Europe, so there was plenty of snow to deal with. This picture was in the Netherlands. And also in the Netherlands, in Amsterdam, René Descartes went out and experienced a snowstorm and observed the flakes closely. And as was his habit, he theorized a lot about it. Here at the bottom are hypothetical precursors of snowflakes, which are little chunks of ice with little hair-like things coming out of them. So his theory was that these hairs then joined together to make the shapes shown above here. So the actual snowflakes can look like stars or like fleur-de-lis, appropriate for Descartes' background, or roses. Notice that these have six-fold symmetry, except these eight-branched ones in the middle, and one wonders whether Descartes really saw any snowflakes that looked like that. He was more into theory than into practice. Then in Copenhagen, 25 years later, Erasmus Bartholinus published his thesis as an appendix to his brother's book about the use of snow in medicine. And in that, he published this figure of pictures of snowflakes that he observed. And just 4 years later, Robert Hooke, in his book Micrographia, drew these pictures of snowflakes. So I was just looking around among these things and Googling, and one thing that I Googled was this advertisement for a CD. Here, this is the CD. It's a very nice reproduction of Hooke's Micrographia, but it was sort of a left-handed compliment in this advertisement because it says snatched snowflakes. Hooke includes an array of snowflakes that look more like caricatures than the real thing. These images are copied, not from nature, but from Thomas Bartholin's De Nivis Usu Medico Observationes Variae in 1661. So the allegation is that Hooke copied these, and you can see that indeed some of Hooke's on the bottom look like Bartholin's from 4 years earlier on the top, like there, or here, or here. So it went on to say, careful study of the images which Hooke published revealed that he himself, who so often accused other people of plagiarism, was not above plagiarism. This was Brian Ford saying this, an English person who's a microscopist, a commentator, and a columnist for Mensa, so he has some authority. But it was interesting to undertake a careful study of this on my own, so I looked at it too to see about evidence for plagiarism. Okay, so there are these ones that we could call herringbones. So this is what Bartholin had published in 1661, and this is what Hooke published. And fortunately, we also have nature because of this guy, a farmer from Vermont, up where it snows a lot in New England, Wilson Bentley. He took the name Snowflake Bentley because he got a camera as a youth, and for the rest of his life, every winter would photograph snowflakes. So he published a book with about 2,500 pictures of snowflakes that he took. And we can leaf through the book a little bit here and see all the different kinds of snowflakes that he took pictures of. And one of these is particularly interesting, that one there, because that's this one. So we have nature as well as Hooke and Bartholin, so we can compare them. So let's look up at the top, and we see there are primary branches and secondary branches. And in Bartholin's picture, they make an angle of maybe 30 degrees with one another. And in Bartholin's other herringbone snowflake, they also make a picture of something, an angle of something like 30 degrees with one another. But if you look at Hooke's, they're parallel to one another. And if you look at nature, they're parallel to one another. Okay? Now, we could also look at the fleur-de-lis of Descartes, which is something like this one of Bartholinus. And there's the picture of Hooke from 4 years later. And here's nature. And we can compare these. So Descartes, in order to get fleur-de-lis, had curved secondary branches. And Bartholin had ones that sloped the other way this time at about 30 degrees. But Hooke, again, had them parallel, and nature has them parallel. And if you look in the middle, you can see a six-fold star. And you can see that in Hooke. And you can see a six-fold star in Bartholinus, too. But it's turned by 30 degrees. Right? So quite clearly, if Hooke was copying, he was copying nature. He wasn't copying Bartholinus, and he wasn't copying Descartes. So I sent these pictures to Brian to get it to see what he thought about that. And he emailed me back. The flakes you chose to analyze aren't the definitive examples, I fear. The clincher is the flake labeled K, which looks like that in Bartholinus and like that in Hooke. He continued, Hooke was careful not to reproduce images directly, but, as was the habit, to make small changes so that he could not be accused of copying, but copy he did. The K flake couldn't possibly be coincidence, and it was assuredly not observed in nature. So I went back to Snowflake Bentley and sent him copies of these two snowflakes. To which he replied, this is an elegant argument, though having looked at a great many snowflakes under the microscope, I am not persuaded. And he continued, Hooke was a particularly pushy and strident character, a man for whom I have unlimited admiration. but I don't doubt that he took Bartholin's pictures as his source. So this raised a question in my mind. And the question was this: who was Robert Hooke? And what did he deserve to do to deserve suffering this reputation for over 300 years? So I began to look at it myself, and I read books. These are all books published since the year 2000. So I'll talk about what I learned there, and I'll talk some about his inventions and instruments and discoveries, and in particular his wonderful book, Micrographia, from 1665. And then a little bit about his work as an architect after the Great Fire of London. And then just a little bit about light and gravity and his conflict with Isaac Newton, which is what suppressed his memory. Not his memory, but the memory of him. And I'll close with a little observation on fame and its transitory nature. And maybe if truth is the daughter of time, how things might be restored again. Okay, so Robert Hooke was 1635 to 1703, so let's put him in context in the 17th century. Here we are in the 21st century. If you go back 100 years, you get to the birth of modern physics with Planck and quantization. If you go back another 100 years, you get to chemistry, modern chemistry, Lavoisier and oxidation. And another 100 gets you to Newton and gravitation, so to classical physics. And then another 100 or 200 years, and you get to Copernicus and Columbus and Luther and the Reformation. And at the beginning of the 17th century, to Bacon's book called The Instauration, which set a pattern for modern scientific investigation. So these things have a lot in common, and they're pointed out by Hooke in the preface to Micrographia. He said, "This 17th century, the current century, was an age of all others the most inquisitive," so that people began really inquiring for themselves into things than trusting the authority of the ancients. Okay, now I had heard of Hooke because I knew of Hooke's law. So he wrote this book in 1678 called Lectures de Potentia Restitutiva, or of Spring. So he devised the law of spring, but that pretty much concluded what I knew about Hooke at the outset. Now, I'd heard of Robert Boyle and Boyle's law. That was very fundamental in chemistry. And he wrote a book that also actually had to do with spring, the spring of the air, about the relationship between pressure and volume of air. And notice that he says that these experiments, physico-mechanical, were made for the most part in a new pneumatical engine. And this engine, shown here in a figure from the book, was made by Robert Hooke. He was the only person who could make it. Boyle, who was a very wealthy person, had tried to have Ralph Greatorex, the best instrument maker in London, make such a pump, and he was unable to do it. But young Robert Hooke, in his mid-20s, fabricated this one, which actually worked. So I'd like to show you a picture of Robert Hooke, but I don't think I can show you a picture of Robert Hooke, although it's conceivable that this figure, which Robert Hooke drew to show the mechanism of a quadrant, an automatic quadrant he made that would track the stars automatically, has someone operating it. And I like to think that this is a self-portrait of Hooke. I have no other evidence that it is, but it certainly could be running his machine. Now we have words to tell about Hooke. Richard Waller, who was his executor, wrote 2 years after his death, describing a person that he knew only in later life. As to his person, he was but despicable, being very crooked, though I have heard from himself and others that he was straight till about 16 years of age, when he first grew awry by frequent practicing with a turn lathe. So he would machine things and bend over all the time. And according to thoughts in the early 18th century, this was the cause of his deformity. He was of an active, restless, indefatigable genius, even almost to the last, seldom going to sleep till 2, 3, 4 o'clock in the morning, and seldomer to bed, oftener continuing his studies all night and taking a short nap in the day. His temper was melancholy, mistrustful, and jealous, which more increased upon him with his years. Now, this is the source of so many people thinking that Hooke was a sort of nasty person. But in fact, he's described him when he was very ill and very late in his life. And in fact, he, as you'll see, he was quite a personable, interactive kind of individual. He was in the beginning very communicative of his philosophical discoveries. Philosophical in that period meant scientific, and inventions, till some accidents made him to a crime close and reserved. He laid the cause upon some persons, challenging his discoveries for their own, taking occasions from his hints to perfect what he had not, which made him say he would suggest nothing till he had time to perfect it himself. So in 1676, when he published the true theory of elasticity or springiness, he published it in this form, right? Which is an anagram. And then when he wrote the book of spring 2 years later, he unscrambled it so that it says, ut tensio sic vis, as the extension, so the force. That is, if you double the length, if you stretch it twice as far, it'll feel twice the force. So many of his things he published as anagrams so that he could reserve the credit without letting other people who were going to steal it know exactly what he was saying. And Samuel Pepys in his diary said this of Hooke: he is the most and promises the least of any man in the world that ever I saw. By promise, he doesn't mean he'll let you have something, and that he means that he doesn't look very promising because of his deformity and so on. But he is the most. Now, Robert Hooke was born the youngest son of a curate, a minister on the Isle of Wight near Freshwater Bay here. He was sickly as a child and was educated at home, and mostly actually by himself. And when he was 13 years old, his father died. He may have hung himself because of his being a royalist at the time of the English Revolution. So Hooke inherited 40 pounds from his father and took off for London with the intention of being apprenticed to Peter Lely, who was a famous painter. He was a very nimble man, Peter Lely. He painted Charles I the year before he was beheaded. He painted Oliver Cromwell, who beheaded him. And when Charles II was reintroduced, he became the court painter and painted Diana Kirk, a painting that's at Yale, and many other ladies. So Hooke could have done this, but in fact he got headaches from oil paint. And also, he thought he could teach himself as well as Lely could teach him. So he didn't do this. He went instead to study at Westminster School under Richard Busby, a very strict person, but someone who was important in educating a number of early scientists. Hooke learned the 6 books of Euclid in 1 week, but he did many other things too. He spent a lot of time in workshops in London learning how to operate lathes and that sort of thing. And he also learned to be an organist in school. So when he went to Christ Church in Oxford in 1653, he had a choral scholarship, which in fact was sort of a sinecure since there wasn't any choir during Cromwell's time. But what he did do was serve as an assistant to anatomist Thomas Willis, who was dissecting the brain and nerves in order to try to find out where the soul resided. His name is in the Circle of Willis, if any of you are physicians and know this structure in the brain. But then he was taken away from Willis, hired away by Robert Boyle, who was in Oxford, to be his lab assistant. And this is where he built this famous pump. And 7 years later, he went to the Royal Society, which had just been founded in 1660 and received its charter in 1662 as the curator of experiments. He was unsalaried because he was still the servant of Boyle, so Boyle contributed him to the Royal Society, and he continued serving as the curator of experiments for the next 40 years. The Royal Society was a group of people, a quorum of them having to be wealthy people to support this operation, who would each put on a demonstration on successive Wednesdays when they met. But these people sort of ran out of experiments to do, so they hired Hooke and asked him to do 4 novel experiments every week for their meetings. Okay, so but one might wonder, because of the fame of Boyle and Hooke and the founding of modern chemistry with this air pump, where in Oxford you find the Boyle-Hooke laboratory. Well, this is the High Street in Oxford with University College on the left, and down there used to be Mr. Cross's chemist's or pharmacy building in which the lab was, but it's not there anymore. If you go there now, you see this, where there's a plaque on the wall that says, "In a house on this site between 1655 and 68 lived Robert Boyle. Here he discovered Boyle's law and made experiments with an air pump, designed by his assistant Robert Hooke, inventor, scientist, and architect, who made a microscope and thereby first identified the living cell." Now, you might think that dome behind it is a little Hooke-Boyle museum, but you'd be wrong. If you go around there and look in, you find it's a memorial to Percy Shelley, who was thrown out of Oxford in his first year. So where is this revolutionary Boyle-Hooke pneumatical engine preserved? The only thing that survives of it is a little tiny piston that is in the Museum of the History of Science in Oxford. Like all of Hooke's other instruments, it was discarded after his death. So here are some of Hooke's inventions. This thing, the universal joint. Have you ever ridden in an automobile? If so, you used a universal joint, which is used to connect the engine to the wheels. This thing, the anchor escapement, which is if you have an expensive watch, that's what controls your watch. Now, it was first used with a pendulum to allow this thing to swing back and forth, but much better, Hooke said, would be a coiled spring, as in this watch, which is the one with which Harrison won the navigation prize that allowed you to tell latitude. But that was 100 years later. But the balance spring in Harrison's watch is exactly what Hooke drew a picture of. Okay, he invented the iris diaphragm. He invented smooth, quiet helical gears. If you just have 2 regular gears like that and run them, they don't run smoothly and they make a lot of noise because a tooth begins to engage and then becomes fully engaged and then begins to release. It's uneven and it chatters. But Hooke had the idea that if you put a bunch of them in a stack and displaced each successive one, then at any given time, there would be one in the beginning phase, the next phase, the next phase, the next phase, and it would run smoothly. And he noticed that the limit of having an infinite number of such gears in the stack would be to grind the teeth on an angle to make a helical gear. And the same car that has the universal joint will have helical gears like this in its transmission. He invented the telephone. Now, not your cell phone, and not the kind of your home phone. He said, "I have, by the help of a distended wire, propagated the sound to a very considerable distance in an instant, or with as seeming quick a motion as that of light." So do you see what kind of telephone he designed? It's a tin can telephone. Okay. Now, he also made a lot of innovations in architecture and building. He designed the Royal College of Physicians on Warwick Lane in London, and in it he incorporated new Hooke windows, different from these other windows that are the classical kind. So do you see what's special about Hooke's windows? They go up and down. So he invented the two-leaf sash-weighted window, which is very widely used nowadays. We have them in my house. Or the dome of St. Paul's Cathedral in London, which in fact is 3 domes. There's an outer spherical dome to denote heavenly perfection, but it's not strong enough to hold up the lantern, in fact, to hold up itself very well. So inside is a conic dome, which supports the weak top of the sphere and the lantern. And beneath it is an inverted catenary dome, a self-supporting arch, which was invented by Hooke. So this is Hooke's inverted catenary arch, which he alluded to at several talks in the Royal Society in 1670, but he published in 1675 in a list of 10 inventions together with that anagram of the spring law. He says, as item 2, the true mathematical and mechanical form of all manner of arches for building, with the true abutment necessary to each of them, a problem which no architectonic writer hath ever yet attempted, much less performed. And then he gives the law, A, B, C, 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 D, D, E, 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 F, G, G, and so on, which wasn't unscrambled until after his death by his executor. And what it is, as hangs a flexible cable, so inverted stand the touching pieces of an arch. So this is the way a chain hangs. So a chain has only tension within it. There's no sideways force any place along the chain, right? Because otherwise it would move. Okay, so it's only stress along it and, of course, gravity. So if you turn it upside down, then again there's no sideways stress, right? Only compression. So the inverted catenary arch has no shear forces. And it's really interesting that Hooke's mechanical analysis, which is done analog, not a mathematical analysis, is perfectly general and applies where mathematical analysis would be very challenging. I don't know if there's an architect here. I don't know how people do arches nowadays. I suspect there's some sort of app to do that. But Hooke did it this way. Suppose you had a building that was going to have an arch like that with a very unsymmetrical load, right? Then you hang a chain but put extra weight on it, and it deforms. And now you turn it upside down, and what was in pure tension before is now pure compression and shearless again. So it's the appropriate design for the shape of an arch to hold up that particular form of weight, and you can make it anything you want by hanging other pieces of chain anyplace. Okay, now some instruments that Hooke devised. A barometer that would show its readout on a dial rather than having to read the height of the column of mercury. Also a hygrometer to measure humidity. It'd be pretty low in some places out in the desert. A weather clock, a thing that measured 5 things about the weather, the wind speed, direction, temperature, humidity, and I forget what the other one was, but made a recording of them in the 17th century. And many other meteorological instruments. A reflecting quadrant with he invented a micrometer screw, the telescopic sight, clockwork drive so it would follow the stars automatically, and the spirit level to make things level. Okay? A device to measure the frequency of fly wing beats. Think how you would do that. Okay? A compound microscope, which is what he's probably best known for. And he said of these instruments, by the addition of such artificial instruments and methods, there may be in some manner a reparation made for the mischiefs and imperfections mankind has drawn upon itself, so that when Adam fell and lost proper contact with nature, there's now a hope of getting back through instruments like microscopes. He made a number of discoveries in many fields. For example, he discovered the spots on Mars and Jupiter, and therefore the fact of their rotation. Chladni figures. Chladni was 100 years after Hooke, but Hooke did this. Do you know what the kind of thing it involves? You take a brass plate here, and you put sand on it. He used flour, and he bowed it with a violin because he had skill with a bow. I didn't, so I used dry ice. So this is pretty neat. Watch this. So Hooke did that and found the different modes of vibration of plates of different shapes. So acoustics. In geology, he made a strong case that fossils weren't lusus naturae, they weren't nature trying to fool you into thinking that something was something else. They were actually the petrified remains of a disappeared creature, so that nature wasn't the same now as at the time of creation. So the idea of the mutability of the earth and of species was Hooke. The idea of continental drift, that Europe used to be far south because of the kinds of fossils he observed in freshwater bay where he grew up. John Aubrey wrote in 1692, so Hooke had communicated to Aubrey his ideas about geology, and Aubrey had written a little book about it and sent a copy for review to John Ray, who gets the credit among geologists for inventing this kind of thing. But Aubrey wrote in 1692, and now lately has come forth a book of Reverend Ray in octavo, which all Mr. Hooke's hypothesis in my letter is published, and without any mention of Mr. Hooke or my book. Mr. Hooke is much troubled about it. 'Tis a right Presbyterian trick. Okay? He demonstrated the role of the lungs in aerating blood, which involved a fairly grisly experiment with dogs that he refused to do again when the sponsors of the Royal Society wanted him to show it to them. The consumption of nitrous air by combustion, that part of the air was consumed in combustion. So here, 100 years before Lavoisier and Scheele, was right on the trace of oxygen. But he was doing so many things that he couldn't follow them all up. Here are 3 weeks during October of 1663 and what he was involved in during that period. He prepared a paper on what should be observed and recorded to make a history of the weather. He made and demonstrated a hygroscope from the beard of a wild oat with an index, that is a dial that could tell how humid it was. He prepared 2 thermometers, one of tin, one of glass, which had been invented by Wren, because the higher-ups in the Royal Society would tell him what to do, and he had to do those, of course, for his employees. See, he was really the first professional scientist. There were many independently wealthy people like Boyle who could do science, but this was his job, his full-time job. He made an artificial eye, prepared a suitable concave glass for projecting a picture in a lighted room, so he made a slide projector. Remove and restitch a piece of a dog's skin to see if it will regrow. This was another suggestion of one of his sponsors, I believe. Supervising making a new air pump and a machine to measure the force of gunpowder. Prepare micrographs of a common fly and of moss growing on a brick. Care for the Society's museum, labeling all the objects with where they came from. Prepare a demonstration of a lineless depth sounder to show King Charles, hoping to get money out of King Charles. That is like writing a grant proposal, and he had about as much luck as most of us do with grant proposals. Graft feathers onto a cock's comb, another suggestion of one of the sponsors. And move house into Gresham College. So he did all this in 3 weeks. This was Gresham College, founded by Thomas Gresham 100 years earlier, an Elizabethan banker, the founder of the Royal Exchange. And it was set up so that there would be 7 professors who live in it without being married, who would give lectures every week on various subjects to the populace. So Hooke, because the Royal Society never paid him, but they tried to find ways they could get money for him, and one was to have him appointed a professor. So he was a professor of geometry who lived in this corner of the quadrangle. So there was where he lived. And there's a very funny structure up here on the roof. See that? And if you look at it in cross-section, it looks like this. And what it is a hole through the roof with a little lid that you can lift up and down according to whether it's raining. And there's an objective lens up on the top, and you can lie down on the floor, on the ground floor, and look through a micrometer eyepiece. So it's a very big telescope. But it has the disadvantage, you'd think, that it can only look straight up. You can't move it. But in fact, that's its virtue. It was called a zenith telescope. It can only look straight up at the zenith. Now, what's the use of that? Well, there was the question of whether the cosmos is heliocentric, whether the Earth moves. So if you look straight up, and if the Earth goes around the sun, and you look at a star at one season, it won't be there in the other seasons, right? And the experiment failed for two reasons. One is that the frame of Gresham College was too unsteady to keep the thing really straight, especially considering how very, very far stars are away. They don't move very much. So the experiment failed. But what didn't fail was his work with the microscope. So in 1665, when he was 30 years old, he published Micrographia, which is one of the great scientific books of all time. Samuel Pepys bought a copy the instant it came out on the 20th of January in 1665, writing in his diary. And so to my booksellers, and there took home Hooke's Book of Microscopy, a most excellent piece, and of which I am very proud. Before I went to bed, I sat up till 2 o'clock in my chamber reading of Mr. Hooke's Microscopical Observations, the most ingenious book that ever I read in my life. Now, the previous year, another book had been published by the same printer on science in 3 books, one of which is microscopical. So we might compare what's in this book with what we'll see in Hooke's book. So here's observation 9 from Henry Power on the little white field spider with short legs. And here you see we could most distinctly see 6, in some cases 8 eyes ranged in this order. So this is the kind of figure that Henry Power had in his book. And 1 year later, Hooke published this picture of a spider, right? A long-legged spider in this case. Okay. Now, the very first picture in the book is of his compound microscope shown here, but all these things are his invention, not only the compound microscope, but the way of making a bright light on it when you don't have electrical power, right? You have a candle fed by the oil and a sphere filled with water to form a big lens to condense it so you can get a bright spot on what you're looking at. And then he has 60 chapters or observations of different things, starting with the very small and going to rather large, as you will see. And the first is on the point of a sharp, small needle. And what amazed him about the needle was how very rough it looked, that nothing manufactured by man when looked at with a microscope was really smooth and clean, but things made by nature were really perfect. Okay, so there was the point of a needle, and just beneath it here, there's a full stop, a period, printed. And he showed what it would look like if you looked at it through the microscope, which is this. Again, what man makes is not at all as perfect as what nature makes. Or what's beneath here is the edge of a razor, which doesn't look very good to work with. Observation 11 is of figures observed in fine sand, of which you have plenty around here, but you don't have this kind that had these funny little pieces of sand in it, which he recognized, and you can see a picture of it nowadays, foraminifer from the Dover Cliffs. So it's the first picture of a protozoan. He realized it was the shell of a fossilized shell of an animal. In observation 13 of the small diamonds or sparks in flint. So these are little quartz crystals, and you see the scale here of a millimeter. So these are fractions of a millimeter, but he tried to figure out where the shapes of these came from. So he did an analysis very much like Kepler's. They arise only, as he wrote, from 3 or 4 several positions or postures of globular particles. So if you put spheres together, you can get shapes like this. If you have 3 or 4 or 5 or 6 or 7 or other numbers, right? And he said, there was not any regular figure which I have hitherto met withal that I could not with bullets imitate. Even almost by shaking them together, he could get these forms that you would observe in crystals, the angles and so on. And he continued, the philosophers hitherto conclude nature in these things to play the geometrician, according to that saying of Plato, O theos geometrei, God does geometry. It's impossible, however, to imitate exactly the curious and geometrical mechanism of nature in any snowflake. So he couldn't quite get that by shaking bullets together. He said, I designed to get as exact and full a collection as I could of all the different kinds of geometrical figured bodies, having such a multitude of instances to compare, as in the solution and crystallization of salts, and incidentally, that's the first use of the word crystallization in English language according to the OED, we cannot but learn plentiful information of the principle which nature has made use of in almost all inanimate bodies. But he was too busy. This passage begins, nor have I hitherto found indeed an opportunity of prosecuting the inquiry he wanted to do. So he just didn't have time to do all these things that his fertile brain kept cooking up. Observation 17 is of petrified wood and other petrified bodies. So the first publication on the idea that these things were originally wood and now had become stone. Observation 18 is on the schematism or texture of cork and of the cells and pores of some other such frothy bodies. And that's the first use of cell to mean a biological unit. Observation 51 is of the crab-like insect. He says, reading one day in September, I chanced to observe a very small creature creep over the book I was reading very slowly. Having a microscope by me, I observed it to be a creature of very unusual form. And that's the picture that he then illustrated it with. Now, this was the subject of a history paper, a history of science chapter in 2008 by Janice Neri, Between Observation and Image. So it's about the creativity of the scientific artist, because she discovered in the British Library this single page in a book filled with other kinds of notes, and noted at the bottom right something that looks rather similar to Hooke's picture in Micrographia. And down at the bottom here, it says R.H. 1661. So she inferred that this was due to Hooke, and then tried to see what went on in Hooke's mind between the time he drew this and the time he wrote Micrographia 4 years later. So she said the surface that the insect creeps across has been transformed from paper, creeping upon paper, into creeping over a book, right? She says Hooke uses the word reading twice, portraying himself as a scholar. He didn't need to convince anybody he was a scholar. When he died, his library was 3,000 books, and very special books too. But the implication is he's trying to put something over on people here. The engraving has been substantially reworked. In the published version, it has 8 legs. Every surface of the body is described in minute detail. So it's likely that he again filled in the missing information from his knowledge of other insects or other species, such as spiders or crabs. In other words, that he dry labbed this picture, that 4 years earlier he made sort of a casual observation of it, and then drew this fanciful thing based on analogy to other things. Hooke may have used the illustration of crabs that appear in Piso's book as a model for constructing his image. And in fact, Hooke did own that book. This is the picture of the crab there. But notice some significant differences. Look at these little cheilifers on the front of Hooke's thing. There's nothing like that on the crab. And in fact, if you go to the book on pseudoscorpions, I corresponded with Gerald Legg, the author, on this subject, and he said this is clearly the Cheilifer museorum. And in fact, in this book, you can look and see that they have exactly the same kind of thing. And at the very bottom, they say the earliest British record is Hooke, 1665. So there's no question he drew this of the real thing, that he was copying nature down at the bottom right, not some picture of a crab. He didn't dry lab. He had more respect for science than that. Observation 54 is of a louse, and it looked like that, and that's Hooke's hair, presumably. Right? And imagine Pepys running into this picture when he had suffered from lice or from a flea. Now, these pictures are really something. Here's the picture in Hooke's book of a flea. Right? So if we look at it here, blow it up a little bit. Imagine if you had fleas and opened your book and saw that this is what you had. Now, the Connecticut Academy of Arts and Sciences meets at Yale, and in 1945 they put out a Festschrift for a biologist there, and one of his PhD students wrote a chapter, Sir Christopher Wren and Micrographia, noting that because the plates in Robert Hooke's Micrographia contributed in a rather large measure to the influence which the book has had in biology, they assume in their own right a place of some importance. So he went on in this paper to say, a priori, there's no reason to assume that Hooke could not well have drawn the pictures himself, for he was apprenticed to Peter Lely and studied with Cowper. And furthermore, many architectural and mechanical drawings which Hooke left give ample evidence of his experience and competence as an artist. Yet, so we won't go through the whole paper, but the conclusion is, in resume, because it is known that Wren and Hooke were associates, that Wren made drawings of insects, and that he was identified with the Micrographia even until its publication, because Hooke talked to him a lot, and because certain of the plates cannot be attributed definitively to Hooke, it seems a reasonable conclusion that Wren contributed the drawings from which some of the engravings were made, among them the head of the dronefly, the louse, and the flea. In other words, that the two most important figures in the book must be to Wren's, because there's no other evidence that Hooke drew them. What kind of logic is that? And in fact, it's quite clear that Hooke did them, that not Wren. There's been a lot of recent scholarship in the last 5 years that shows that clearly they're Hooke's. Okay? Now, and you don't even need that. If you go back to the Philosophical Transactions of the Royal Society, number 2 from 1665, so just 2 months after the book came out, this was edited, and most of the articles written by Hooke's neighbor, who was also his bête noire. They didn't get along at all, Henry Oldenburg, who was the secretary of the Royal Society. But Oldenburg wrote, in representing these particulars to the reader's view, the author hath drawn all the schemes of these 60 microscopical objects with his own hand. And he was much more inclined he would have been much more inclined to give credit to Wren than to give it to Hooke, because Wren was much higher among his bosses, right? So it's quite clear that from the very beginning that these must have been Hooke's. But there's if you look any place, if you look at a rare book auction that includes Micrographia, you'll see that it says that some of the figures were probably drawn by Wren. There's just no basis for this. Okay. He hath also suggested such conjectures as are likely to excite and quicken the philosophical heads to very noble contemplations. Here are found inquiries concerning the propagation of light through different media, concerning gravity, and so on. So Hooke in this book not only had observations he made through the microscope, but many new theories. For example, the last observation, number 60, is of the moon, this picture that I showed you previously. And he contrasts his image of the moon with the run published by Hevelius 10 years earlier, or 15 years earlier, which is certainly not of the same quality. And you can tell that Hooke's is good because if you compare it with a photograph taken from an orbiting station, you can see that it's exactly tracks what's really there. And Hooke, but there is more to this chapter on the moon than that. He says, to conclude, therefore, it being very probable, the moon has a principle of gravitation. That is, what caused these things? It must be things falling into the moon, right? So he made experiments with ground up pipe clay and dropping balls in it to see what shapes you would get. So he was interested in whether gravitation was universal, not something special to the Earth. So we search after the cause of gravitation. Now, something related to that is in observation 58 on the inflection of rays of light in the air. He noticed by astronomical observations that the rays of light curved as they went through the atmosphere, as you see here. Right? So, and he said the reason is that the density of the atmosphere varies with altitude, which causes light to curve as it goes through it. And he did experiments to show that that would be so. And then to do a theoretical analysis, he said, we will suppose a cylinder indefinitely extended upwards, so an infinite cylinder filled with air, and we'll look at the density at different heights. But he says, I say a cylinder, not a piece of a cone. Obviously, if the Earth is a sphere, what's above a given point is a cone, not a cylinder. And he says why he does that. Because, as I might elsewhere show in the explication of gravity, that triplicate proportion of the shells of a sphere to their respective diameters are supposed to be removed in this case by the decrease of the power of gravity. That is, what he says is that the area in the cone increases according to r squared, but if the force of gravity decreases with 1 over r squared, then you can cancel those things out and pretend that it's a cylinder. Right, so he's talking about the proper law for gravity. Now, this book, that's in Micrographia, that was written in 1665. So in 1665, a student read this, took lots of notes on it, and then went home because of the plague to Woolsthorpe. And you probably know who that person was because he sat under this apple tree and the apple fell on his head and gave him the idea of gravity, which he had just read in Micrographia. Okay. Observation 9 was of the colors observable in Muscovy glass, that's mica and other thin bodies. So he has this diagram showing mica of different thickness, and he says pulses of light, that light is a series of pulses, that it comes in and gets reflected like that, but some of it goes through and gets reflected from the bottom, right? So what actually comes out is pairs, strong, weak, right, at a certain distance in time from one another. And that the mind understands as yellow. But if it's thicker like this, then there's a bigger space between them, and the mind sees that as red. And if it's still further spaced, then what you see is a weak pulse followed by a strong pulse, which the mind understands as blue. Okay? So he had the idea that light was pulses and that these colors came from the pulses, which isn't so very far from the ideas we have now of waves and their diffraction. But the other person, Newton, did his experimentum crucis a year later and let light go through a prism and then cleverly drilled one hole in that board so that only red light could go through the second prism, and wrote nec variat lux fracta colorum. The broken light does not change its color, so the second prism doesn't do anything to wouldn't do anything to the timing of Hooke's pulses. So he concludes that light is a substance, not waves. And he considers this his crucial experiment to prove that it's a substance and not waves. Of course, we know that there's a lot of subtlety in understanding light, but Hooke certainly had a good idea about it. So Newton wrote to Hooke in 1676, what Descartes did about colors was a good step, and you have added much several ways, especially taking the colors of thin plates into philosophical considerations. If I have seen further, it is by standing on the shoulders of giants. Now, in saying this, he was actually quoting Lucan's Civil War from 62 AD, and which had also been quoted by Burton in Melancholy. So it wasn't original to Newton to say that, but it was particularly poignant because Hooke was hunchback, so the idea of standing on Hooke's shoulders may have stung a little bit. Now here's London in 1666 in Gresham College, where I said Hooke lived, and in the first week of September there was the Great Fire, which just almost burned up Hooke's house. But it's an ill wind that blows nobody good, and it created work for Christopher Wren, who made 51 churches and St. Paul's Cathedral after that. But Hooke was also involved. Wren represented the king, but Hooke represented the city and the guilds and so on in designing new buildings. So, for example, at Moorfields nearby, Hooke completely designed and supervised and selected the material, every aspect of the building of Bethlehem Hospital, which, as you know, is Bedlam. He also designed and constructed the monument to the Great Fire in 1677, which is Monument Stop on the Tube. It's quite large, as you can see. There's Charles II for scale down at the bottom. And there's a basement. How unusual to have a basement in a monument. And up at the top, it turns out there's a hatch that can be opened up. Now, why would you have a basement and why would you have a hatch? Because if you open the hatch and lie down in the basement, that's what you see. right? It's a 215-foot zenith telescope to see whether the Earth is orbiting the sun. Unfortunately, it also wasn't stable, and when carts would go by in the street, it would move enough that you can't make the proper experiment. Now, if you go to the monument nowadays, you see, I photographed this 2 years ago. The monument designed by Sir Christopher Wren was built, blah, blah, in the Wren Church and so on. So Wren gets all the credit for doing this. And why? Because in 1750 was published Parentalia, or Memoirs of the Family of the Wrens, beginning with Matthew, Bishop of Ely, but chiefly of Sir Christopher Wren. And you can see that it was compiled by his son Christopher and published by his grandson Stephen in 1750. So not surprisingly, it focuses a good deal on Christopher Wren and his work. So it says here, with respect to his work in architecture after the dreadful conflagration, Dr. Wren was appointed Surveyor General and principal architect for building the whole city. But it was a lot of work. A charge so great and extensive, incumbent on a single person, disposed him to take to his assistants Mr. Robert Hooke, professor of geometry in Gresham College, but that Wren reserved all the public works to his own peculiar care and direction. In the year 1671, the surveyor, that is Wren, began the building of the great fluted column of Portland stone of the Doric order, commonly called the Monument, in London, in memory of the burning and rebuilding. Prior to this, the surveyor Wren, as it appears by an original drawing, had made a design of a pillar somewhat less proportioned. So he did design the monument, but it wasn't the one that was built. Hooke designed the one that was built. Right? So the monument, says a modern critic, is undoubtedly the noblest monument column in the world. So that father and grandfather Wren was responsible for this. Now Hooke, as I said, wrote to Newton to try to get him to contribute to the Royal Society. And he said, "I hope that you will please to continue your former favors to the Society by communicating. You may be assured that whatever shall be so communicated shall be no otherwise further imparted or disposed than you yourself shall prescribe. I'm not ignorant that both heretofore and not long since also there have been some who have endeavored to misrepresent me to you. But difference of opinion, if such there be, especially in scientific matters where interest hath little concern, methinks should not be the occasion of enmity. Let's be friends and collaborate," he says. I shall take it as a great favor if you shall please to communicate by letter your objections against any hypothesis or opinion of mine, and particularly that of compounding the celestial motions of the planets of a direct motion, that is the inertial motion, and an attractive motion toward the central body, that is gravity, that is get the orbits by inertia and gravity. Okay. I should be glad if by perpendicular observation, that is using the zenith telescope, we could determine the difference of latitude between London and Cambridge. So you do it in Cambridge, I'll do it in London, we'll find how far apart they are. Let's get together and do things. So Newton replies, "I cannot but acknowledge myself every way by the kindness of your letter, tempted to concur with your desires. Heartily sorry I am that I had for some years last been endeavoring to bend myself from philosophy to other studies." I'm not really doing science anymore, unless perhaps at idle hours sometimes for a diversion, so I can't collaborate with you. I did not, before the receipt of your last letter, so much as hear that I remember of your hypothesis of compounding the celestial motions this way, which is the way he's going to do his calculations, or of the cause of springiness, which had been published for 2 years by this time, though there's no doubt they are well known to the philosophical world. And Hooke annotated the letter this way: "Here pretends he knew not Hooke's hypothesis. My own short-sightedness and tenderness of health make me something unfit for doing these perpendicular observations. So I don't think I'm going to be able to work with you. However, I'm going to suggest a problem about that has to do with whether the Earth rotates. And we're going too long here, so I'm going to zip through this and just say, here's the letter Hooke wrote to Newton, which is in our library at Yale, in which he says, "I wish I were as sure of your correspondence in communicating as I am of your remaining affection to philosophy." That is, I don't believe for a minute you're not doing science anymore. And on the back he draws a diagram that shows how Newton has not analyzed the problem properly and should do it a different way, and another diagram that shows the same thing. And Newton is very embarrassed. That was December 9th. So quickly, Newton, let's skip over this. Newton draws back that this should be the path that the thing would take falling. If there was a vacuum in the center of the Earth. So shortly after. And Hooke responds to this on January 6th. Your calculation of the curve described by a body attracted by an equal power at all distances from the center, so a constant force, is right. How did he know it was right? Right? Because Newton used his calculus to figure it out. How did Hooke know that he got the right answer? Because Hooke did an experiment that showed that's what it was. And this is a repeat of the experiment by a physicist, Michael Nauenberg, a few years ago, which is to take a cone where there's a constant force to the center and roll a ball in it and see what trajectory it takes. So it's an analog way of doing the problem. But, he says, my supposition is that the attraction always is in duplicate proportion to the distance from the center reciprocal, not a constant force toward the center. That is, the force should be inverse square law. This will spoil the universal standard of the pendulum. He was worried that because the Earth isn't a perfect sphere, the pendulum won't have the same frequency and can't be used in a clock to measure latitude. Then he writes again on January 17th, I doubt not, by your excellent method, calculus, you'll easily find out what the curve must be with the inverse square law and its proprieties, and that you will suggest a physical reason of this proportion, why it should be an inverse square law. And Newton responded to this almost 1 year later. And what he said was, I am indebted to you thanks. That's all he said. Okay, now, several years later, Newton was finally encouraged to publish the Principia Mathematica, right? Notice, incidentally, the imprimatur is from Samuel Pepys, who was the president at that time of the Royal Society. But he was reluctant to do that and was talked into it by Edmund Halley. Now, Halley then showed the manuscript to Hooke and wrote back to Newton, Mr. Hooke has some pretensions upon the invention of the rule of the decrease of gravity being reciprocal as the square of the distances from the center. He says you had the notion from him, though he owns the demonstration of the curves generated thereby, that is the application of calculus, to be wholly your own. Mr. Hooke seems to expect you should make some mention of him in the preface. So Newton writes right back to Halley and says, Hooke has done nothing, and yet written in such a way as if he knew and had sufficiently hinted all but what remained to be determined by the drudgery of calculation and observation, excusing himself from that labor by reason of his other businesses. Whereas he should rather have excused himself by reason of his inability, for 'tis plain by his words he knew not how to go about it. Now, is this not very fine? Mathematicians that find out, settle, and do all the business must content themselves with being nothing but dry calculators and drudges, and another that does nothing but pretend and grasp at all things must carry away all the invention. So what did he do? Right? He dropped references to Hooke from the manuscript and downgraded others. For example, where he had written Clarissimus Hookeus, the most distinguished Hooke, he took out Clarissimus. Okay. Now, we won't go through this, but this is how Hooke used geometry to prove Kepler's laws and to have a source for the inverse square. So there was a little mistake in it, but he almost did it geometrically and with a physical reason for the inverse square law, which Newton just asserted. But one last thing I'm going to mention about it was Hooke's studies of medicine, iatrochemistry. So this is from his diary from the year 1672. August 1st, also 2nd, 3rd, and 4th, drank iron and mercury, was ill. August 31st, slept ill by reason of tart at noon, got up a little, rectified my stomach with white aniseed distillate. September 1st, drank steel, benumbed my head. At Dr. Goddard's, tasted tincture of wormwood. Took 2 ounces of infusion of crocus metal, which I think is sodium antimony sulfide. vomited, took syrup of poppies, slept little with sweat and wild, frightful dreams. October 1st took spirit of urine and laudanum with milk for the 3 preceding nights. Slept pretty well. Took conserves and flowers of sulfur, after which I slept well, but had a bloody dysentery the next day, so I swooned and was violently griped. But I judge it did me good for my room. Made oil of bitter almonds, put some in right ear. Slept ill. But my favorite is that he lived another 31 years, but doing the same thing. For example, 17 years after that time, he gave the Royal Society the first comprehensive description of the effects of cannabis, which had been brought from India by his sea captain friend Robert Knox. And in describing it, he said, "This I have here produced is so well known and experimented by thousands, and the person that brought it has so often experimented it himself that there is no cause of fear, though possibly there may be of laughter." So, he became an MD the next year. He died in 1703 at the age of 67, with 8,000 pounds in a chest under his bed, which is as much as a merchant banker would have had in those days, enormous sum, which he made from his work in architecture after the fire and surveying, but no will. So a lawyer and an illiterate distant cousin soon went through his estate, or at least through his published estate, right? Because 9 years later, his long-term assistant, Harry Hunt, and his executor, Richard Waller, contributed 1,200 pounds to build a new home for the Royal Society, which neither of them could possibly have had. So they had opened the chest under Hooke's bed when he died without a will. So almost certainly this 1,200 pounds came from Hooke to build the new building of the Royal Society. So Waller published the posthumous works of Robert Hooke. That is, lots of things that Hooke hadn't had time to publish in his lifetime, in 2 years after he died. And as you see, these posthumous works of Dr. Robert Hooke are humbly dedicated by Richard Waller, Secretary of the Royal Society. And who are they dedicated to? To Isaac Newton, Knight, President, who died 25 years after Hooke. So he had the pulpit for another quarter century. And here's his monument in Westminster Abbey. He became president of the Royal Society the year Hooke died. After Hooke died, he didn't want to do it while Hooke was still there to criticize him. Right now, there are 4 books he's leaning on. The bottom one is the Principia, and then Optics, which he published 1704, the year after Hooke died, because he knew what Hooke would say about his publications on optics, right? But the top 2 are occult books. One is about the chronology of ancient kingdoms, showing that Solomon's temple was the first temple and every other temple was designed after that. And the other one was about divinity, interpreting the book of Revelation and so on. And John Maynard Keynes, who purchased Newton's unpublished work on alchemy, which was very voluminous, 300 lots, not pages, 300 lots in a Christie's sale, said Newton was not the first of the age of reason, he was the last of the magicians. Hooke was the one who was the first modern scientist. Okay, but Newton got all the credit and saw to it, and probably also saw to it that the portrait that had been painted of Hooke disappeared. So there was a portrait of him, but there is no authentic portrait now. They don't even know for sure where Hooke is now. His remains probably lie in this mass grave, having been moved there from St. Helens Bishopsgate when they wanted to remodel it in the 19th century, because no one knew who Hooke was anymore. Newton had been so successful. But in the 19th century, a German firm had put in a window to commemorate Hooke with this image of him, but no one knew what he looked like then. And even that window you can't see, because typical with Hooke's luck, it was blown out by an IRA bomb in 1992. Right? So what about Gresham College? Well, it's not there anymore either. It's under NatWest Tower 42. So, other than Hooke's writings and drawings, very few mementos survive. There are no contemporary memorial or portrait, almost no experimental apparatus, just that one little thing I talked about. None of his greatest architecture except Wren's monument to the Great Fire and 3 parish churches and a country house. But we still have Hooke's London because he was the one that was responsible for the way the London was laid out after the fire. And his Royal Society, which would never have succeeded without Hooke. And his writings and discoveries and inventions. And here is a list by Hooke of his accomplishments. He says the theory of motion, theory of light, theory of gravity, theory of magnetics, theory of gunpowder, theory of the heavens, improving shipping and watches and optics and engines for trade and engines for carriage, inquiry into the figures, the shapes of bodies and the qualities, the properties of bodies. So Hooke's reputation has been resuscitated by, among others, principally Robert Gunther, who wrote 14 volumes on early science at Oxford, and 5 of them are Hooke, right? Louise Deal Patterson published 10 years later on Hooke's gravitation theory and its influence on Newton, and Margaret Espinasse wrote a comprehensive biography of Hooke in 1956. And Ellen Tan Drake wrote Restless Genius, Robert Hooke and His Earthly Thoughts. That is, his contributions to geology, only geology. That's this book published by Oxford Press. It's 400 pages about how much original stuff in geology Hooke did. Now, I think it's very interesting that 3 of these 4 people are women who know what it means to be discriminated against over the years, probably. So the fact that Justice is a woman, I think, probably is not irrelevant here. And another woman is Rita Greer, who since 2003 has painted 17 portraits of Hooke to give to different institutions that were associated with his work, so they would have portraits of Hooke. Right? And in 2005, finally he got carved into Westminster Abbey in a pavement which he, in fact, had supervised the construction of. And in 2007, the Great Fire monument got this memorial to Hooke added to it. And in 1723, there was this monument to Christopher Wren, who was buried right here. And it says, beneath this building lies the builder of this church and city, Christopher Wren, who lived beyond his 90th year, not for himself, but for the good of the people. Reader, if you seek his monument, look around you. Now, since 2009, if you looked around, you would see this. Robert Hooke, 1635 to 1703, one of the most ingenious men who ever lived, Fellow of the Royal Society, Professor of Geometry at Gresham College, Surveyor to the City of London, friend and colleague of Sir Christopher Wren. And written around it is a quote, and it's taken from observation 52 of the small silver-colored bookworm. Remember, Hooke was a book collector. And what's written around there from this observation is, it appears to the naked eye a small glittering pearl-colored moth, which upon the removing of books and papers in the summer is often observed very nimbly to scud and pack away to some lurking cranny where it may the better protect itself from any appearing dangers. So the idea of the hunchback Hooke trying to get out of trouble.